Justin Ratto took them down. He was our moral conscience or something like that. But anyway, here's the notion is that if we look at a distant star, but not too distant, because this really only works out to a few hundred light years, okay, we can actually do parallax angle on them. But if we look at a star and we look at it in July or, for example, January, right, okay, or June or January, anything that's 6 months apart, we're going to be on opposite sides of our orbit, right? So you just pick, if the star's over there, then we're going to pick this, whatever that month is and whatever this month is, right? So we're opposite sides of our orbit. We can use the astronomical unit now as a baseline to do parallax on a distant star. And the relationship is that the distance is 1 over the parallax angle. And this is really pretty tough mathematics. You notice we've saved some of the tougher stuff for later in the year, right? So the distance, and then they literally say parsecs in your data packet, right? Okay, is 1 over p, which is the parallax angle, in arc seconds. Okay, so arc seconds are 1/3600th of a degree. Yeah, so basically, if it's 50, it's a degree is 60 minutes is 3,600 seconds, yeah? Right? And we talk about minutes. Minutes are double thing, right? A minute is a second, a minute is a single thing, and a second is a double thing. And I get those confused, right? Did everybody see the movie, This is Spinal Tap? Yeah. Yeah, okay, and this is Spinal Tap. You know, besides my amplifier goes to 11, right? There's the scene where they want to make, they've got this song about Stonehenge, right? And they want to make a model of Stonehenge and have these dancers dancing around it, right? It's like, in the time of the Druids, you know, right? And so they hire this artist to build a model of Stonehenge. She's never seen Stonehenge, so the guy draws a picture, right? And he goes, well, it's just these stones, and this is about 30 feet, right? Only that's not feet, that's inches. That's actually feet. Right, so she builds the model actually 30 inches tall, right? They get the model and it's like this big, right? So to make it look big, they hire midgets to dance in front of it, right? I don't know. It's one of the better scenes, right? Or that, or they've got these pods that they're supposed to come out of for some song, and the bassist can't get out of the pod, so he's trying to play inside the pod. Now, take a look at this. What this says is that the farther something is away, the smaller the parallax angle is. Yeah? So let's do that thing again. Okay? Cover your left eye. Put your finger out here. Block some distant object. I'm blocking the NASA sticker. Now cover the other eye. It shifts a little, doesn't it? Now put your finger a little bit closer. Block the same object about halfway to your face, right? And then take and block the other eye. It shifts more, doesn't it? The closer it is, the bigger the parallax shift. Now put it like right here. Block the same object. It shifts even more, doesn't it? That's crazy. So the more it shifts, the closer the thing is, right? Yeah? Isn't it funny that somehow a distance is 1 over an angle? How could that be? How could we not use like inverse tan or tangent or something like that? It's such a small angle that all those trig functions basically just become, I'll show you. Okay, we'll do it the way you think you ought to. We'll do it the way that they say to do it. We'll get the same answer. Okay. Now, here's a diagram again, and notice that if you draw this thing here, if here's the orbit of the Earth, right? Here's the Sun, here's the Earth, right? Here's the l'étoile lointaine, right? The distant star, right? I got this wrong on the IB test. Maybe you've gotten to that question, right, where they say the distance in parsecs. I thought that the whole thing was the parallax angle. I forgot that this was the parallax angle, right? So this is what P is half of that total angle. Kind of makes sense. I don't know. Maybe it doesn't. Okay. Let me show you. This is an actual picture of a parallax measurement. So again, the way that you measure parallax angles is not with like a protractor or something like that. Okay. What you do is you actually look at where the star is relative to the background star. So this is a very accurate, the telescope is zoomed way in on these stars, so they're actually smearing around on there. Why are the stars, why do they look black? It's a negative picture of it, right? Okay, so astronomers don't, they're just trying to get data, so they're just looking at the negative of this. Now watch, I'm going to toggle back and forth between two images. One of those little blobs moves, the other ones don't move. Why don't the other ones move? They're way far away and the motion of the Earth is insignificant, right? They are thousands and thousands of light years away. This only works up to maybe 1,000. The North Star is one of the ones we can get parallax for. It's 660 light years away. Okay, so check out this little guy here. This guy moves back and forth. Now, let's suppose that this is 10 arc seconds. I have no idea what it is, right? This distance here would be about 2 arc seconds. I mean, literally, you measure that distance, or as we say in academic circles, a graduate student measures that distance literally on the film and uses simple ratios. This distance is to this distance, as these are two well-charted stars. We know their exact positions, degrees, minutes, seconds, right? And we just subtract, right? And we can get the parallax angle in there, right? And of course, the more you zoom in, the better your telescope is, the more the field of vision is a smaller angle. That's how it works, right? Okay, so that's how we measure. Here's an example. A star has an annual parallax of 0.037 seconds. What is its distance in parsecs? Well, we can do that, right? The answer is really simple. If we use the distance formula, and this is what you should do. If they say given in parsecs, use the parsec formula. So 1 over 0.037737 seconds, and it already is in seconds, this is D is in parsecs, yeah. And they tell you that it's parsecs. They tell you to use arc seconds, so it's like a bonus formula, right? So 1 divided by 0.037 is 27 parsecs, right? You can abbreviate it. You can go 27 PC if writing the other 4 letters is too hard for you, right? Okay, so 27, I guess, is probably not capitalized, right? Okay, and then the second thing you can do is that we can, the Earth's radius, the Earth's, okay. Now, we can also figure it out. Let's figure it out in kilometers. Don't we know that this distance right here is 1.496 times 10 to the 8th kilometers? Don't we know that? Don't we know this angle here is 0.037 divided by 3,600 degrees? Don't we know that? Yeah. So can't we just use tangent to find it, as you think you'll need to do, right? Okay, so let's figure it out. This is the adjacent side. This is the opposite side, right? So if the tangent of the angle is opposite over adjacent, then the adjacent side is opposite over the tangent of the angle. Isn't that right? So we can figure this out. 1.496 E8 divided by the tangent of, and then it's a really small angle. It's even small in seconds. So 0.037 divided by 3,600. Right, so let's do that. 1.496 E8 divided by the tangent of 0.037 divided by 3,600. What mode am I in? I am in degrees. Okay, this is good. Okay. Got to make sure I'm in degrees, right? And I get that it's Is that right? Anybody else get that? Oh, I did inverse tan. What am I doing? I'm like, I don't recognize this number.
I don't know, Ron. Sounds kind of weird.
There we go. I recognize this number. Why am I doing inverse tan? I always think in my head that there should be an inverse. I'm getting 8.34 times 10 to the 14